How have you been?
Been alright, mate.
Yeah?
Have you?
Yeah, I've been alright.
Close enough.
Yeah, it should be spot on.
Oh, okay.
So I've got Phil today. If you want to give us like a bit of a background of where you come from in terms of science or what you're into at the moment.
Well, where I come from, my mother, my parents, of course, in general. No, pretty much same place you come from.
Yeah.
We met at secondary school, didn't we?
Yeah.
In, what's the teacher's name? Reading class, actually, wasn't it?
I
think that's where our friendship first went off.
Where we struggled through school.
Absolutely, we did struggle through school. I think, like I say, back at school, I think obviously we're going to go down the science route, but back at school I wasn't really interested. I was interested in sports, running, you know, it was, and then women happened, beer happened.
Women happened, yeah.
You know, you get your confidence and that's it.
Yeah. Change your focuses a lot, don't you, at school?
Absolutely, mate.
It's funny how that works, isn't it?
So, I mean, I think for me, it was when I left school and I had the freedom to look at what I wanted to look at, not what school was trying to shove down your throat. So, from a science point of view, it was always been interested in astronomy.
Okay.
Always been looking up, you know, that sort of thing. So, astronomy's always held a deep space in my heart, if you like. Like I say, I never pursued it or anything because I don't think I had the tools necessary to pursue it. And when I left school, worked at McDonald's, and that gave me the freedom to mainly looking into astronomy and galaxies and how the solar system works, and then you know that opens the doors up to more things like you know, you finally understand why people get nicknamed Einstein if they're clever. Because you finally start to understand the work he did and quantum mechanics and them sorts of things, how it all molds together, all the way back to Newton and Galileo.
Will Galileo being the first? Yeah.
Galileo, yeah, him. Like I say, science it's a progressive thing. You know, like Galileo was, I'd say he's the grandfather of physics.
I'm gonna say
or science in general.
Yeah, he's kind of known as like the forefather, isn't he? The beginner of it.
Yeah, absolutely. And I think what a guy. And then I'd say Newton built upon his ideas and formulated his three laws of motion. Gave the name of gravity a concept. You know, the whole story of a fallen apple.
Yeah.
Whether that choice is true or not, I presume he saw an apple fall, and then that's how the whole.
That's how the legend goes, isn't it?
That's how the legend goes, absolutely, and what a legend it is. And obviously, between that and then we had Faraday, you know, who was discovering electricity and magnetism and being able to see the connections between them two, and James Clerk Maxwell, Scottish bloke who saw, you know, recognised what Faraday was doing, was able to derive the laws mathematically, because I think Faraday wasn't very mathematical. He had extremely great practical skills, like experimental skills, and you know, Faraday is one of the people I'd be very envious of, because he lived in a time where he was discovering when you pass a current through a wire, it gave off a magnetic field, and you're like, oh, what's going on? And he could do all the experiments, and that now are trivia. If you understand, you know, it's still amazing experiments and still extremely cool phenomena. But man, to be at that point where he was like thinking, you know,
where everything was new.
Yeah, and it wasn't just it. There was a few other scientists that, you know, put their work forward. But then, like I say, and then that that Maxwell equations had the. Obviously, we then get into the speed of light, because Maxwell was able to predict that electromagnetic waves, and that these always travelled at one speed, which we now know is speed c, which is the speed of light, which is constant in a vacuum. Well, it's constant, but in a vacuum, it's the cosmic speed limit. And no matter what you do, no matter where you measure it from, the speed of light's always the same for every observer.
Mm-hmm.
It doesn't matter if you're going, if I'm going 20 miles an hour and you're stationary,
Okay.
we both turn a light on, that my light doesn't get 20 miles an hour faster.
Mm-hmm.
It's just the light, it's various ideas that take place which have been backed up experimentally.
Mm-hmm.
Like saying, this is where Einstein comes in. Einstein was always thinking about light. That's what led him down his path, was this mystery of light. Like people, because people are so used to Newtonian mechanics
Okay.
that it didn't seem to be right that the speed of light was always the same no matter what.
Mm-hmm.
And there's various ideas like the luminous, I can't remember the exact name now, the lumosphere. Basically, like you see water travels through a medium, like a wave travels through the water.
Mm-hmm.
So they reckoned, or if sound travels through air, it travels through some medium and vibrates. That was a concept. Like maybe light travels through a medium, vibrates through some ether. That was it. Luminous ether. So they reckon as we orbit the sun, you'd be going one direction and this ether will be pointing one way, so the light will be travelling next speed, and on the other side of the sun, obviously you're travelling the other way against the ether, so it'll be travelling at a different speed. But they found that no matter what they did, the speed of light was always the same. And that's where Einstein then developed his ideas of relativity, which obviously flew in the face of Newtonian physics. So he unified, in a way, the ideas behind gravity and the speed of light, because in Newton's idea, if the sun suddenly disappeared, the Earth would be shot off its orbit immediately.
Okay.
But the light from the sun is still going to take 8 minutes to get here.
Yeah.
So therefore gravity's travelled faster than light, so therefore light isn't a cosmic speed barrier.
Okay.
But what we find through Einstein's general relativity is when if the sun suddenly disappeared, it'd take 8 minutes, so it travelled at the speed of light.
Okay.
So
they're like fundamentals of.
Yeah.
Because I know
absolutely.
so Einstein's known as like the. If Galileo was the first, he was like picking up where he'd left off. Basically, it's like a building block scientist, isn't he?
Absolutely. But at the same time, as Einstein was coming up with his ideas, like the branch of quantum mechanics was also being discovered. So the subatomic world, what goes on with electrons and protons and neutrons and the atomic world, which actually Einstein won his Nobel Prize for, because he was it's for the I can't remember the name now. Anyway, he won an idea that was to do with quantization anyway, packaged particles, and also he discovered that there's something called Brownian motion. If you get a pollen grain and put it in water, look through it through a microscope, you can see it's bouncing around, even though you see this pollen and it doesn't look like there's anything around. So that's how he was able to then come up with some calculations to predict atoms are actually what's causing it to move and bump around. And obviously quantum mechanics is the single most best theory we have in science. It's what's allowing us to do what we're doing now, and then for later on for you to broadcast it across wherever you'd like to broadcast it to. So I think it's all that progression. You need the underlying knowledge.
Yeah. I was going to say I quite like how the field is moved on by new ideas. So it takes somebody to have a groundbreaking thought, and then maybe people that were on the outskirts of finding something or that was looking for something themselves, the work from one field spills over, and then all of a sudden it's possible that now we have an answer for something else that someone else was asking. Do you know what I mean? I like how they cross-talk. I like how they work in tandem with each other, and that's part of the reason why I find it so interesting, is because it's like a pursuit of constantly asking questions and trying to piece together what makes the most sense.
Yeah, absolutely.
And like you mentioned Galileo and who was the other one you was on about?
Newton.
Newton,
Faraday.
Faraday.
Yeah.
One of the questions I was going to ask you is you mentioned that he didn't. Did you say he didn't really come from a mathematical background?
No, because he was a bookbinder originally.
Okay.
Back then, it was like you sort of like whatever your parents did, you'd fall in like you'd do the same. So if your father was a blacksmith, you'd most likely become a blacksmith. Faraday's parent was or father was a bookbinder, and he got an apprenticeship in bookbinding. But obviously, he was passionate about learning. He wanted to understand. Fundamentally, his drive was he believed in a supreme being, and he wanted to understand how the supreme being
controlled everything.
Yeah, made the world work. So he read. He went to. He got tickets to go see Sir Humphrey Davy, who was a famous experimenter back then, and he got to see his lecture, and he made notes on his lecture, and he went and he showed Sir Humphrey Davy these notes he'd made, and he was very impressed and took him on as an apprentice and as a student, if you like, and eventually, obviously, Faraday became the master. And
just from pure observation?
Just from experimentation and observation, yeah.
See, that...
He knew basic maths.
Yeah.
But he didn't really need it back then. He needed to know a ground in maths.
See, one of the things with Einstein is it's like a common fallacy that he wasn't very good at mathematics when he was younger.
Yeah, absolutely.
Everybody says that he wasn't good, but he was good at maths.
I mean, clearly.
It's
obvious in his works. And
see, somebody once, I think I watched a documentary and they were saying that they thought that he wasn't good at maths because he struggled to do simple maths when he was younger, and so there was a thing with him where he was good at complex maths but not simple maths, and then there was something where he apparently failed one of his I think he was like it would have been like maybe primary school going into secondary school, he'd failed an exam.
Yes. Yeah.
But the big misnomer with it is that the test that he did was in French, and the actual mathematical side that he did was spot on. Like he'd passed that. It was the talking about how you'd worked it out that he failed on, because the test was in French. So there's a lot of things that go around about maths and getting into science that isn't necessarily true. But the reason I bring it up is because we're going to talk about a great man that's just passed away. And he apparently, he was, he come from a mathematical background, and that's how we got into science. I was going to ask you if you thought that you have to have a fundamental knowledge of mathematics to jump into science.
I think
physics.
So obviously, we're on about Stephen Hawking.
We are, yeah.
Let's name drop him.
Yeah.
And I think these days it is imperative that you do know mathematics, because the way physics is going now is it's following the maths, and it is complex maths. And like anything, maths is a language. It has to be learnt. Just like you don't expect to, like the same with Einstein and French. You don't expect to walk into a French class and then walk out of that same class being fluent after one lesson. And it's the same with maths. It takes years to develop the fundamentals, which then all build into your more complex stuff. If you're just going to try and jump straight into calculus and you don't know algebra or geometry, it's going to make your life so much harder. Do you know what I mean? So it is literally learning the fundamentals and getting into this. Now, not all types of physics requires you to know mathematics. If you're an experimentalist, you won't need to know all the mathematics. I mean, it's good to have an understanding of how these work, but a lot of the time you're running programs, and you know what you want the outcome to be or expect them to be, and whether the experimental data shows that or not, it's neither here or there.
So these guys, they're living in the head more than they're doing the equations.
Experimental physics. Well, there's experimentalists and then there's theorists.
Okay.
Hawkins was a theorist.
Mm-hmm.
He formulated the ideas. He come up with the mathematics that would make predictions that experimentalists can test.
Okay.
So it's important that experimentalists do understand the mathematics, but I mean, personally, because a lot of people, I think, people have a genuine interest in learning physics and science, but then they get scared by the maths. And all I can say is it is hard. It is hard. You have to work at it. And I mean, I left school with a C in maths at the foundation paper level, not even a higher paper level. I left for a few years and I come back to my education, and I've now done my degree in electrical engineering, which I managed to obtain a first. And I put that first down mainly because the math side of my degree I focused on, and I learned the underlying maths of how. I mean, a lot of people on my course would try and just hammer through it without understanding the basics. Now they're all very clever and they all knew what they're doing, but it's that emphasis on making sure you know your maths, because if you don't, you're not gonna. Unfortunately, you're not gonna get very far in the field.
Similar, that I was talking about learning different aspects of mathematics. It's kind of that same thing with science, where you was on about the ideas spill into each other.
Yeah.
So I mean, if you're very rudimental about certain types of maths that you can do and you haven't mastered them all,
then
absolutely, it's going to hold you back, isn't it?
Yeah. I've lost my train of thought here.
So he was talking about your progression through maths through school.
Yeah, but to bring it back to science, and you need it at the forefront of science. I mean, I think you need to know it in chemistry and biology, not as just to the same extent as what you do in physics, but maybe even more so, because biology is so much more complex than physics in some ways, because there's just so many variables in biology. It just gets so complex. And in physics, you're dealing with balls, basically, just different size, with subatomic electrons, which are like point-like particles, not even balls, but we represent them as like little circles, if you like, or to planets, which are just big balls.
Okay.
Sorry, and and that's, we can make a lot of we can use the maths very. Let's look at LIGO. LIGO is the.
Can I just interrupt you? Why do they use a spherical idea as what we think of as atoms and planets?
Well, for planets, it's obvious because
that's the shape.
That's the shape of the Earth, or the shape of planets.
But on a subatomic level.
On a subatomic level.
Is it just that is just the way to represent them, or is it they are that shape?
Ultimately, you can't really zoom in enough to see an atom. I mean, to be fair, I don't really know, so I don't want to give you
false information.
Yeah, false information.
And everybody false information.
Yeah, absolutely. So, for electrons and subatomic particles like quarks, we think of them as point-like particles. And even photons, which are massless, we still think of them as like little particles, but then we get into wave duality, where it's a particle or is it a wave.
Oh, you mean the double slit experiment.
Yeah, what a fantastic experiment. So yeah, it gets into that whole territory there. That's why we can't really say it's a little sphere, because, well, at one point it might be, but then at another point it's... And I don't know enough about it to give a definitive answer.
Okay.
I can tell you what I know about it and how extremely fascinating it is.
So just on a basic level, so that experiment is... The reason why it's thought of as moving both ways is because it changes when it's observed. in the experiment.
Yes, absolutely. So if we go from the start of this double slit experiment, so you have a glass of lead or something, I don't know, a shield, a guard or whatever, and it's just got 2 slits in it, and you fire electrons at it, and you put a detector on the other side. This detector will pick up what's known as an interference pattern, and this is what we get with wave-like behaviour. You get your peaks, and they add up to your high points, and you get troughs, which make your low points, and then you get the ones which are directly opposite, which cancel each other out. So sorry, no, they're your troughs because they cancel out. Anyway, we see this interference pattern. Now, originally what they thought, they were sending all these, maybe they're interfering with themselves. You're sending a flood of electrons through, maybe they're interfering with themselves. So let's fire one at a time. And what happened was you got this, because it was assumed that electrons were particles at the time, and then what you got was this interference pattern again. So it was like, oh, hey, electrons are waves, and then what they decided to do is like, right, let's put a detector on each slit and see which one it goes through, and then you get the classic particle picture on a detector. You get two lumps where the electrons has gone through because you've measured them basically, and the act of measuring changes the result. It's not some consciousness. It is consciousness measuring it, so it's determining what the outcome is. But fundamentally, you've got to measure it some way. So you've got to shine a photon onto what you're measuring, which then interferes with that electron going through. So then you've given it a definite position in space. So that's why we get this difference, if you like. And then you take the detector away, and it goes back to being a interference pattern. And it's a beautiful, and the same thing with light.
Is it photons. So it's a mystery still?
No, it's very well known and understood within quantum mechanics. Like it's very well understood, and I mean that's why computers work, because we understand how the electrons. I think it was, who was it? One of the great scientists. I can't remember which one now, but he said he says, oh yeah, great, we know what electrons are now, but what use will they ever be? And now we're sat here with all this computer technologies, mobile phones that
jump the technology forward.
Exactly, and that's all because of quantum mechanics.
So Schrodinger ties into that, doesn't he? To explain why he's trying to explain why they they can operate differently. Is it?
I can't remember exactly what Schrodinger's ideas were.
So it was the Schrodinger's cat.
Oh yeah, that's it. Cat can be dead and alive. Yeah. Right. So.
Meaning is it to do with superpositions, isn't it?
Superpositions, yeah. So a particle could be in more than one place at a time. So I think the best explanation I saw was actually that documentary I was on about with Brian Greene, an American physicist, and he did a documentary. There's two actually. There's The Elegant Universe and The Fabric of the Cosmos. And I can't remember which one it's from, but I think it's from The Fabric of the Cosmos. And also in his book he explains it. If you did a countdown wheel and you spin it and it got a ticker on it. If let's just say you replace that with black and white sections, the ticker could land in a black slot or the ticker could land in a white slot. Now if you put one of them on the moon, and you spun the one on Earth, and the other one would be spinning as well, if this one stopped on black, the one you immediately know what the one on the moon is. It'd be white. It'd be the opposite.
Yeah.
This is more about entangled particles.
Okay.
But I think the idea of superposition is electrons experience this. I don't fully understand it, but they experience this property called spin.
Okay.
Spin up or spin down. But before you measure it, before you know what spin up or spin down, it's in a superposition. It's
one or the other,
or both at the same time.
Or both, yeah.
And this is where qubits come into it, and that's way out of my depth. But
okay.
Yeah. So.
So might it be that we haven't got the right technology to measure what position that they're in?
Yeah. Well, it's funny. Measurement. Let's just talk about measurement. Is a finite source, if you like. you can only measure something to a certain degree of accuracy.
Mm.
That's why science will never claim to know the 100% truth about something, because you can always measure something to an extra decimal place.
Okay.
Do you know what I mean? You can't have infinite accuracy. So there's always errors creeping in your measurements, because our instruments of measuring can only finitely. Now they're amazing these days. You know, like I mentioned LIGO a minute ago, detecting gravitational waves.
Mm-hmm.
And the instruments in that machine are extremely sensitive. You have to take into account people walking their dog a mile away. The vibration,
Really?
Yeah, the vibration sent through the earth. It all gets picked up, and we have to mathematically, and well, obviously it's all done with software, cancel all that out just to pick up these movements.
The small.
Yeah, that's it. And so measurement's always a changing factor in science. How can we measure something better, more accurately?
Okay.
And then what were we? Main point about that was what?
I don't know. Went off in a tangent.
Yeah. But I wanted to make sure measurements.
Measurement's a big deal.
Nothing, like we were saying a minute ago, building ideas. Science is about building ideas on the generation, or the people.
Oh, it was
before you.
we were talking about entanglement. So he was talking about how he was talking about how this guy had a different analogy for it, but we got onto it because of Schrodinger.
Yeah, that's right. He used the cat example. So he explained it as like, you have a cat in a box with a vial of poison, and this vial of poison was to activate when a uranium atom decayed or something. Then once this radioactive isotope decayed, it will set off the vial of poison, and the cat will either be dead or alive. But because we can't see it, the superposition, we've not measured it. It could be thought of as being both until we open the box and observe, make the measurement, and observe what's actually gone on. And that's like, probably a bad overview, but there's plenty, like I say, there's plenty of information out there to look in to get a better understanding of that particular idea, if you like.
I know if you come from a religious persuasion or a spiritual persuasion, a lot of part of science, people maybe shouldn't use science to explain or disprove a religious element, but I know a lot of religious people try and use science, and they'll use the mysteries in science to prove their side. And I know that he was talking about consciousness with, was it electrons you was talking about? Was it protons with the slit experiment? Photons?
Yeah, it's the act of measuring. I think Feynman famously said that human consciousness is the atom contemplating itself, because we're made of atoms, and we're looking at atoms, trying to figure out how they work and what have you. But
so beautiful.
Science doesn't concern itself with supernatural explanations, because they are precisely that. They are beyond natural, hence supernatural. What I can say is, if an idea you're putting forward to science, science can't explain it. Science might not be able to explain this idea yet. As soon as it does explain it, whatever this idea might be, it ceases to be supernatural, and it becomes natural. It becomes part of science. And this is this whole argument, and I don't think a lot of people use it anymore unless they're not really familiar with the arguments. It's called the God of the Gaps, or the supernatural of the Gaps, shall we say? And if you're gonna play that game, it's gonna fall within ever smaller windows. And science is, science is progression. But science doesn't claim to know the answers to everything. And the most honest answer you can give, which hopefully I've done a few times here, is I don't know. There's nothing wrong with not knowing. If you want to know, you'll go find the answer. It's extremely lazy, in my opinion, to put a supernatural causation on it.
To stamp it out and say it's this.
And say it's that. Yeah, just say I don't know. If you personally want to believe that, that's fine. Don't go thinking that the science is against you because it doesn't agree with your idea.
Mm.
That's ridiculous. Science doesn't care what you think. Nature doesn't care what you think.
Mm.
The world is a world, you know. Nature doesn't care. If you're driving your car recklessly and you hit a wall at 80 miles an hour, nature's not going to go, oh, let him get away with this one.
Yeah.
You know, you might survive. You know, you might survive unharmed. That doesn't mean a supernatural agency saved you or something intervened to save you. It just means that this highly unlikely probability of you falling in that way happened. I mean, there's 7 billion people in the world. This is going to happen at some point. If you say this supernatural agency saved me, well, what about the kid that died 6 weeks ago in the same accident?
So it's like rolling the dice, isn't it? It's like
it's
working the chances out of certain things happening.
Absolutely.
There's always that one where it doesn't happen.
Always, yeah. That's the thing with probability. It's, it's that way, and you know, I like to say, you know me well enough now to know that I haven't got a problem with people believing in supernatural things, but why are you coming knocking on my door? Do you know what I mean? You know, but people do what people do. You know? And people, as Magneto said, people always fear what they don't understand.
Yeah. Out wherever you want, back off.
I mean, well, we'll start on the line of skepticism, because that's also something that's become an idea quite close to my heart. Is mainly because of science, my joy for science and critical thinking and skepticism becomes part of the package. Like, so well, I don't really know what more to say really. What I've already said on that.
So in terms of that, from your background, when you started at school, you are your background is from a religious point of view.
Okay, yeah.
Obviously, time with knowledge, time with science has changed that for you.
Absolutely. So yeah, when I was at school, I was an altar server. Catholicism, believed in God, prayed, and all sorts, you know, like that. And I think for me, it wasn't a sudden no, I don't believe in God. I went through the whole phase of questioning God. And funnily enough, it all started at school in sixth form.
Okay.
When I was brought up to say you can't question God. Of course God exists. Don't be silly. But then it was actually philosophy at school who said, and we were actually questioning the idea of the creation of the universe. I didn't really fully understand them then. But looking back, I understand them, and I think I always say, I wish I had the knowledge now and I could go back, but I don't, because I'm in a pretty nice place, and you know, events unfold how they unfold. But,
you kind of owe that teacher for your point of view now, don't you?
Miss Janino.
Yeah.
Yeah, maybe. Yeah, do in a way. Yeah, she says.
She's the first one to ask you a question.
Yeah, so it's everyone questions God, and it was like, well, at the time I was like, oh, of course God's real. You're being silly, you know. I mean, I can remember being in a philosophy class and thinking, looking out the window, you know, from South Block, the older one, and looking up to North Block, and I looked at the trees and I thought, oh, trees breathe out oxygen, and we breathe in oxygen. There's got to be some
perfect mechanics.
Yeah, exactly. You know, but then you got to think, well, how does the oxygen get here in the first place? It's like, well, the trees make it, and then oxygen and living things come later. You know, but that aside, and there's simple explanations to explain such mechanics, if you like. But yeah, so it was a you know, like, it's like, suppose thought crime. It was like I was watching what I was thinking. I was watching the way I was questioning God. Like, I was like, yeah, of course you're real, God, you know, and saying I'm sorry for questioning him. That sort of like level of indoctrination. I don't think my parents ever meant to. They just did what they thought was right for me. Yeah. Which is great, and also they had the goodwill to make sure I developed my own mind. If you like, and they've never pressured me to stay fundamental about my religion. So I guess that freedom of thought, and it was science. It was science in general. I think in a way, I just forgot about the whole idea of God. science made sense to me. I didn't really... God never come into the equation, if you like. It was only when what I found was skepticism became important to me when I had witnesses turn up at the door. And they had an answer for everything. I was like, what about it? And they had an answer, and I thought, what? You're not understanding something in science here. Yet you have this answer, and I couldn't reply. I was like, well, yeah, they're doing exactly what I'm doing. I'm saying one point of view, and they're giving me a point of view back. I believe I was fighting from the point of view of science and what we know, but then how I was just stood there chatting to them. I can't exactly whip out
textbook
and start saying, look, and they were the same, you know. They were well, in fact, they had books, you know, and it was interesting. I took the leaflets from them, and you know, this is where it started really skepticism coming to mind, and then obviously I went through. Learned about Richard Dawkins, Christopher Hitchens, and that's where the idea. So I guess my skepticism starts with the whole concept of atheism. I don't like the term; it gives you a label. Like
a lot of atheists don't like the term.
No, because it's like it's what they give to us. It's a label they give to us. I like the label skeptic. I'm skeptical of any claim. I think we said the other day, you know, like anti-vaxxers, people who don't vaccinate the children, and you know, and it's this whole idea we have that no one can be offended. And I love Ricky Gervais's new comedy, Humanity. Have you seen it?
We started watching it the other night. Yeah, it's really good.
I think
really
his
good.
ideas on that whole sensitive issue, he nails it. He nails it hands down.
I watched him on a chat show, and he was talking about people's right to be offended. And he was like, yeah, it's your right to be offended. He was like, but it doesn't mean that I have to follow that. Exactly. You know what I mean?
The thing is if it offends you, disengage yourself.
Yeah.
You know, and also as he says, if it offends, feel lucky that you can feel offended. Because if you, I mean, when it comes to a discussion of what people believe in the supernatural, people have different ideas. You will never find a definitive answer as to what God is. You know, put it in a container for me. People have the different. Oh, God is love. God is trust. God is woolly terms
and it sure changes from one God to another as well a lot of the times, doesn't it?
Yeah,
from one religion to another.
Yeah, absolutely, and from person to person within that religion,
what their experiences are and stuff. Yeah,
and like I say, it's a matter of thinking. Let's, you know, what's the most likely answer? That's what science deals with. What's, you know, it could be, you know, this lady got cured from cancer from a supernatural cause, but we should be able to measure that. You know, I think it's Michael Shermer who first presented this idea to me, and if God comes in, jiggles the atoms to get rid of your cancer, we should be able to measure that. But cancer's go into remission. Just because you don't know, you can't then say it was this. Because you don't know how the pyramids were built. It doesn't mean that aliens came and did it. I mean, let's face it. You know, the pyramids is a pile of rocks. You know, when people, it annoys me when people say, "Oh, we couldn't make them." Yes, we could. Yes, we could. We just don't have the. Why? Why do we need?
Well, what was that? We couldn't make them today. Is that what you're going to say?
Yeah, people say we couldn't make the pyramids today.
Okay.
Yeah, okay. You know, you're living in a dream world. Of course, we can make them. We make skyscrapers that make the pyramids look exactly like what they are, the rocks. And it's great. It's a great achievement by humanity. I'm not saying it's not.
I think their thing is you couldn't make them today using their techniques back then.
The thing is, we don't know their techniques. We don't know all of their techniques.
Well, obviously they did. So obviously you could. Like, it's going to be a myth.
Yeah, obviously they did it. There you go. And that's going back to the point. Is I don't know. There's nothing wrong with saying I don't know.
See, I've always thought that they shouldn't really go hand in hand with each other. Where I don't think they should ever be up against each other. I know, like, a lot of people like to use them to clash. They like to have this is my point of view, this is my point of view, and they go head to head. And I don't think it's very. I think that with religion, it's so fundamental to have a point of view or a stand, because you like you said before, you're indoctrinated, and sometimes you find it yourself, and then I think that can be even more strong, because then you've gone and found something yourself, and then you feel connected to it. But I don't think that they should be ever against each other, because I don't think you should use science for that. I don't think that's what science is for.
No, exactly. And I think this whole idea, like you say, if you have a religion, that's great, good for you. But if you're going to push that onto the next generation and not offer them alternative explanations, so let's take evolution, because that's a big controversy in this area normally.
Yeah, it's where it starts, isn't it?
Yeah.
The argument starts with evolution.
Absolutely, always does. Now, you could believe in creationism or some alternative idea, but what predictions does that make? Evolution has made plenty of predictions. It's the backbone of biology. We understand how genetics work with it. At all times, but it's not just like one line of evidence. It's all these branches, all these lines of evidence. Like you said earlier, they all spill into each other and they back up each other. And this is the thing about science: it changes, it tweaks. You know, the theory gets stronger, it changes as new facts become available. You know, the theory's altered. That's one of my favourite Sherlock Holmes quotes. Is when he's talking to Watson and he says, one must obtain all the facts, because if you don't obtain all the facts, one begins to skew facts to suit theories instead of theories to suit facts.
Yeah,
absolutely fantastic. I think I would say that wasn't a direct quote, but I love that sentence because it's true. You need to observe what the facts are, get your facts straight, and then incorporate your idea to explain how these facts work, and then that idea should be able to make a prediction about something else we don't know yet. So let's go back to Einstein and relativity. When he formulated his special theory of general relativity, he made a prediction that starlight will be deflected. As light comes around the sun. So during a solar eclipse, they got the measurement devices up, and they could see, I think it was 1.7 arc seconds it was out by, deflected by the sun. So it proved his idea. That was a prediction he made. Now he already knew that his calculations fitted what we already knew from Newton, but then he made a prediction that light will be deflected because the way space warps and how his general relativity is relayed into reality, which is still surviving today 100 years later after it was formulated with the, like I said, with gravitational waves. What a guy, do you know what I mean?
I think you touched on a point there where I watched a documentary about Einstein, and when he came up with that prediction, I hope I'm not mixing my knowledge, but I'm sure that the first time they tried to record it, I think they tried to record it 3 times, that experiment.
Yes, the first 2 times they failed.
Yeah.
How frustrating that must have been.
Through natural...
I mean, there's also, I think, when you look at the orbit of Mercury, I think it's called perihelion, when it's its closest point to the sun, perihelion phase. That moves with Mercury, because it's so close, and so using Newton's physics, it was like when you look at Mercury and when it's orbiting the sun, and you just say, right, I'll be able to predict it popping out from behind the sun now. It was always off by a few. I can't remember exactly. It was off. The measurement was off, and it wouldn't appear too soon. I can't remember which way around it is. But then Einstein used his general relativity, and he calculated the orbit of Mercury as it went around the sun, and it was spot on. It matched perfectly. I think that was his first real insight, and then he wants to make a direct observation with something else. So it makes many predictions, like the prediction of gravitational waves, black holes, when they're orbiting each other, getting closer and closer and closer, and finally they merge. You know, the gravitational forces involved, it then sends out this shockwave, like dropping a pebble in a water in a pond, and then we can now detect these, and that's another prediction that his idea is still making today. Now, this is the thing about science and theories. All the evidence that we know in the world would never prove him to be 100% correct. But it would take one, and I think he said this himself, but it would take one piece of evidence to destroy his whole idea, to overthrow him. And this is where new ideas come in place. Like I say, with, and this is where, going back to what we're meant to be talking about, with Stephen Hawking's.
We'll get into that in a minute.
Yeah, he was looking for a theory of everything.
Yeah.
But at the moment, you can't unify gravity, general relativity, with quantum mechanics. Special relativity has been unified with quantum mechanics, but general relativity you can't.
Okay.
The mathematics breaks down. It produces anomalies, if you like, infinities.
So that's from one scale to another scale, isn't it?
Yeah. So
subatomic versus like what we can observe.
The macroscopic, if you like.
Yeah.
So planets, solar system, you and me.
But we know that they're both right, don't we? In terms of how we measure them.
The thing, we know that we're more confident that quantum mechanics, or QED, quantum electrodynamics, is fundamentally correct. It explains everything apart from gravity.
Because, like you said before, we use it for computers and stuff, don't we?
Yeah, exactly, and it's phenomenal. But then, general relativity, some ideas in there have to be right, otherwise GPS wouldn't work. Time dilation, we've measured it. The Large Hadron Collider, muons, as we send muons around the Large Hadron Collider, they live longer in our reference frame, therefore time dilation, and then that's also evidence for length contraction. I suppose that's a brief overview. What are muons? This and either. But
what about gravitational force? Is that pretty much that?
Yeah, the best explanation is to use general relativity, and it's like, I think the classic example is always using the surface of a trampoline. If you put a cannonball or some heavy object in the middle of that trampoline, it warps the surface of the trampoline. That's what mass does to space. Like, so imagine space is this, it's a three-dimensional trampoline, if you like, and not just a surface, but it's got the depth to it as well. So it's a bit. So think of Interstellar and the black hole, how that looked. So
it's what people think is like space fabric, isn't it?
If you like, it's
like a type of grid, like a type of
three-dimensional grid. That's right. And you put mass, an object with mass inside that fabric, it warps it. It causes it to bend, and that's fundamentally. So when you throw on this trampoline, there's a cannonball in the middle, and you throw a marble, and it will go around it, and that's fundamentally what the Earth's doing around the Sun, or the Moon around the Earth. It's falling into its gravitational well. So it's not this.
Like the mass has an actual weight to the space around it.
It's sort of like deflecting it, if you like. So space is now being pulled inwards, if you like. Yeah,
because how I'm thinking of it is like if you pulled a cloth tight and you put a marble on it, it would dip, wouldn't it, under the weight?
That's right.
So that's kind of the analogy that I'm trying to move with you on.
Absolutely, that's correct.